Okay, so here's the second attempt at 8C. Here we're going to be graphing the conservative force that produces the potential energy curve. So that's the question. I'm going to actually do this question on the previous graph just because it's way easier to do it that way. So again, this is how I'm going to go through this question right here. So there's several ways, there's several challenges that we're going to have, conceptual understanding challenges that we're going to have to be clear on before we can even begin a question like this. This potential energy change through this graph is caused by a force, a conservative force. So if you think about it, remember that any change in potential energy is caused by work, the work done, which means that any change in this potential energy, which is U in this case, is going to be FD. Okay, so one of the ways we got to think about this is a conservative force. So if the PE of a system is going down, that means that the kinetic energy must be going up, right? If the object is going downhill, it's speeding up. Conversely, if the potential energy of a system is increasing, that means that the kinetic energy must be going down. So here you can see that the changes on potential energy and kinetic energy are of the opposite sign. That is sort of the first conceptual idea that we're going to have to be clear on. So I can see now that, my previous video just saved. So the way we can look at this now is that if we're going to sketch the force is equal to, and I'm just going to call PEU just because that's what it's doing right here. The delta U over delta X. Remember, X is D, by the way, like any change. X is a delta X. D is delta X, excuse me. I'm in danger of an iPad not allowing me to do this one because I'm being incoherent. Anyways, as I just mentioned, this opposite relationship means that there got to be a negative value here. All right, this is the engine that's going to drive this graph that we're going to draw. This is the key understanding that our force is really going to be of the opposite value of the slope, the delta U over delta X. It is, again, the force graph is going to be of the opposite value of the slope of potential versus X. All right, so I'm going to erase some things right now. I'm going to keep this idea, but I'm going to rewrite it up to the top a little bit lighter. Okay, this is our main idea, and we'll probably have to refer to that a few times. Okay, so whenever you're trying to graph, I find it's easier to graph on top of the other graph just because it's really easy visually to see where these inflection points are. I want to point out that this problem has a lot of calculus flavor to it, meaning that as you work through this problem, anybody with background in calculus will recognize ideas and really get understand what some shortcuts and they'll really have a deeper understanding of a problem like this. However, I'm going to teach it as if there's no background in calculus because the AP test doesn't require calc, and neither does the AP class that I'm teaching. So even though there are calc understandings in a question like this, it's not required. So I'm going to try to steer away from calc words because you should be able to do a problem like this without any calc background. Okay. That being said, let's begin. So the focus here is on the slope. The force graph will be the opposite of the slope of this U versus X graph. Let's look for some inflection points. Inflection points are points where the slope changes, or another way of saying that is, where is the slope on this particular graph 0? Well, the slope is 0 right here. It's 0 right here. It's 0 right here. And this is a little bit harder, but let's just kind of approximate it as being 0, like right there. Like, let's just approximate it. So these are very, very important points for our force graph because those are points where the force graph has to cross 0 because the slope is 0, and that's what the force graph is. It's the opposite of the slope of this graph. So what we're going to do is we're going to put big points at 0 at these moments right here. And let's go right down here. This one's more of an approximation on this one. It's a little wonky over there. Okay. So now that I did that, I'm going to sort of erase these little points right here. Otherwise, because I'm going to have a lot of little points on this graph, so the less I have, the less confusing it will be. All right. Now, the best way, what I wouldn't say the best way, the way that I find most useful is to take a look at what's happening to the motion in between these inflection points. So let's just start with a simple idea. Let's just say what's happening between here and here. Another way is what's happening with this line right here. Okay, this line, if you look, it looks pretty uniform. It looks pretty standard, meaning that this that it looks like it's a smooth function. It's not wonky. It's not, you know, it's not jiggity or whatever you want to call it, jagged, jiggity. I don't know what that is. Anyways, so this is going to be pretty easy to approximate. Let's just say that the average slope is going to be found right in the middle. And remember, we are absolutely focused like a laser on slope. Because that's what the force value will be. So what is the slope at this midpoint right here? Well, it's going to be the average slope from here to here. Again, you might sense, you catch a whiff of calc in there, but I'm not going to go that far. So what is the average slope from here to here? Well, at this position right here, the y value is 1. And at this position right here, the y value is -2. So, and this x distance is 1. So if you think of the slope, it's going to be -2 minus 1 all over 1, which is -3. Okay. So what that means is if the average slope from here to here is -3, that means that the force has to have a value of +3 at this midpoint right here, because that's where I'm approximating. I'm using the average position, right? So I'm going to approximate it. So we're going to put a point at 3 right here. And let me just actually erase some of these little things I did. So we're going to put a point at 3. Okay, that takes care of that little section. Now let's look at this section from here to here. Also looks kind of uniform. I mean, it's kind of uniform. I mean, there's a little wiggle, a little waggle in there. So whenever you're doing these graphs, you are always approximating. Let's pick the midpoint between here and here, and let's just ballpark it to say right there. What is the average slope from there to there? Well, this value would be -3. This value is a +1. And it goes from, let's just, I know it's not exact, but let's approximate it a distance of 2. I mean, yeah, it's slightly less than 2 because that's right there. But let's just go a distance of 2. So this goes 1 minus a -3 all over 2. 1 minus a, yeah, that's right. So this would be 4 over 2, which is 2. So the slope there's 2, which means that our slope from here to here, our average slope, has got to be a -2. So let's put this is our value, right? Let's put a -2 right there. And again, I'm going to erase the work as I go just to keep this thing as tidy as I possibly can. So we will have a point at -2 on our force graph right there. And now you can start to see this is the process that you're going to have to do to graph out this fx function. Or sorry, this fx with respect to x. So now let's do this first section. This first section from here to here also looks pretty uniform. So let's just pick a midpoint. It's going to be around 1 from 0 to, so midpoint will be around here. So what is the average slope from here to here? From here to here? Well, it ends at -3. Starts at +10, and it's a distance of 2, so it looks like -13 over 2, so -6.5, which means that the force graph has got to be a +6.5 in terms of its value. So at this midpoint right here, let's go 6.5. Okay. Aha! Now this last part is going to get a little bit wonky. Notice that from here to here, this is definitely not uniform in terms of its structure, in terms of if you imagine a function. It's most likely not going to be. It might be a two-piece function. So what I'm going to do is sort of the essence of calculus, which is I'm going to break this into smaller pieces and analyze two different sections that seem to be a little bit more uniform, oopsies, by themselves. So I'm actually going to take a look at from here to here first, and then I'm going to look at from here to here. Now, those two things taken separately look a little bit more look a little bit more smooth. So let's do the first section. So from here to here, what's the average slope right here? Well, it goes from -2 to 2 over a space of 1. So -2 minus 2 over 1 is -4, which means that so it's -4, which means your slope is, let me rephrase that. So, oh, sorry, I had that reverse. It's 2 minus a -2. So it's 2 minus a -2 all over 1, which is a positive 4. Yeah, 2 minus a -2. Positive 4. That's what happens when I try to not write it down, by the way. Get a brain fart. And it is 9:55 at night anyways. So this is a 2 minus a -2 is positive 4, which means that the slope has got to be a -4. Sorry, not the force value has to be a -4. So the -4 value at this midpoint right here is going to be right there. So let me erase that work that I did. Okay, and now I'm going to take a look at the piece from here to here. So that's really this part of the curve right here. I'm going to pick a midpoint right here. It's going to look like, let's just pick it right around here. What is the slope right there? It is going to be 3 minus 2 all over a span of, I'm going to approximate it as 1. I can, because again, I'm just approximating here. And it looks like this is going to be 1, which means that the force value would have so double check, 3 minus 2 is positive 1. So it should have a -1 right here. So this would be -1. Yeah, -1 right there. And notice that at this point, the slope is 0, so that's just going to stay at 0. Okay. So that was a little bit painful in terms of describing coherently, but hopefully you understand the essence of what I'm saying. Now we just connect with smooth lines. Here we can see wee, whoop, wee, and it goes wee, like that. And so here's our graph of the conservative force, F. And this is, if you want to be super fancy, F with respect to X. Now we can just double check that to see what the answer, if the answer key likes that. And it should look pretty similar. And yes, you can see right here that it looks like wee, and that is exactly, and by exactly, I mean not exactly, what we have right there. All right, so that's how we graph the force from a potential energy graph.